video, we're going to talk about projectile motion. A projectile is anything that is launched and then follows a path that's determined by gravity. In other words, after it's launched, the only force that will be acting on it is gravity. We won't consider any kind of air resistance or wind, or that won't be a true projectile. Examples are things like kicking a football, throwing a baseball, hurling a rock, shooting an arrow from a bow. Once you've thrown it, or once you release that bow, the only force acting on it's going to be gravity. Now, the puzzle of how to treat projectile motion was actually figured out by Galileo, and the key thing is simply that horizontal motion and vertical motion can be treated separately. They're independent of one another. Well, what does that mean? It means that what's going on horizontally doesn't change what's going on vertically. Let's give a sort of a brief explanation of this. Consider my fingers a little fictional gun here, and in my other hand, I have a bullet. Now, if I shoot the gun up, and at the exact same moment I drop the bullet, everybody understands that the dropped bullet's going to hit the ground first. If I point my gun down at the same time I drop the bullet, fire the gun, drop the bullet, well, obviously the bullet that's fired out of the gun's going to hit the ground first. So with a little thinking, you think, well, what if it was just barely above horizontal? Well, the dropped bullet would still hit first. Well, what if it was shot just barely below horizontal? Well, the fired from the gun bullet would hit first. So it makes sense if I fire a bullet horizontally and I drop a bullet, that they actually both hit the ground at the same time. That horizontal motion doesn't change how long it takes for the bullet to fall. All right, so let's think about this. We treat X and Y, which is short for horizontal and vertical motion, separately. Now, key thing that's going on horizontally is that the acceleration is going to be zero. We don't have any force of nature that causes things to I realize wind and things, but if we don't have air or we don't have wind, there's nothing that's going to cause something to accelerate horizontally. However, vertically, everything accelerates at negative g, or negative 9.80 meters per second squared. The rest of our initial conditions are going to depend a little bit on the problem, whether or not we're looking at something that's thrown horizontally, whether or not we're going to look at something that's maybe kicked up at an angle like a football, or hurled down from the top of a cliff. All of those are examples of projectile motion. Usually we can break projectile motion into two general categories. Let's look at the first one, and that's going to be a horizontal. If we launch horizontally, let's draw a picture. If I launch horizontally, that means that the object has to start at some initial height. I can't launch horizontally from the ground. Now I can launch something up at an angle from the ground. Okay, so it's going to look something like this. It's going to start at some initial height, call that y0, with some initial velocity, I'll call that v0. And the path that follows actually looks like this. It's exactly half of a parabola. You probably remember the word parabola from your algebra days. So the path is a parabola, but this is actually the maximum point. It's like we're looking at only half of it. This distance, this initial thing, is also sometimes talked about as the height. How high was it? And this horizontal distance traveled is called the range, or x. A lot of times we want to know how far horizontally this projectile is going to travel. So that's kind of a picture of what it would look like. If we're talking about horizontal motion, the initial horizontal velocity is just the initial velocity because we're launching it horizontally, we're throwing it in the x direction. If we're talking about vertical motion, it's exactly like being dropped because it doesn't start off with an initial velocity vertically. That v0y is actually 0. Same as dropped. So vertically, this looks like free fall, just like dropping a bullet. Except if we shoot it horizontally, it's also going to have some horizontal motion. We usually let the initial position just be 0, but our initial position over here, y0, of course is the height we drop it from. So we know all of our initial conditions, and these initial conditions are going to change our formulas a little bit because we're going to have some places we're going to add in some zeros. But these are constant acceleration problems. The acceleration due to gravity is a constant negative 9.80. The horizontal acceleration is actually a constant value of 0. All right, so what's that do to our equations? Let's look at a problem. Well, I'll tell you what, let's think about one more thing before we do that. Even though x and y are independent when we solve our problems, it is obvious from this that horizontal motion is going to stop when the object hits the ground, when the object lands. What determines how long this object is going to be in the air? Well, time is obviously determined by the initial height. The vertical motion will determine how long it's in the air. The higher it is, the bigger this number, the longer it's going to take to fall to the ground. So the longer that horizontal motion will continue. All right, so let's go on. Let's look at an example. Suppose that we have a stone and it's launched horizontally with an initial velocity of 15.0 meters per second. And I do want to make sure we know that's horizontally. From a cliff, I'll tell you what, let's just say from a height of 44.0 meters. That's our situation. We could draw a picture. Here's our object. It's got an initial velocity horizontally of 15 meters per second. It's got an initial height of 44.0 meters. It's going to follow a path that looks like this. If we want to think about our known quantities, it's always good to think about what we know. Horizontally, we know the acceleration is 0 because we don't have horizontal acceleration. We know our initial velocity is 15 meters per second because they said it was launched horizontally. And we know our initial position is 0. If we come over here and think about vertical motion, we know that our acceleration is -9.80, and that's meters per second squared, but I'm a little out of room. we know our initial velocity in the y direction was 0. When we launched it, that velocity did not have a vertical component. And we know our initial height is 44 meters. Again, I don't really have quite enough room, but we're good. All right. There's a lot of questions we might want to know. How far did it travel horizontally? How long was it in the air? How fast was it going when it hit the ground? Those are all really good questions. Generally, let's just see what we can figure out. Let's start with time, because we're not going to know how far it travels horizontally unless we know how long it's in the air. And how long it's in the air is determined by vertical motion. So let's look at our constant motion equation, our constant acceleration. Y equals y0 plus v0 yt plus 1/2 acceleration in the y direction, t squared. We're only interested in vertical position, vertical speed, vertical acceleration. All right, well, the initial was 44 meters. The initial velocity vertically is 0. A common mistake is for students to put in that 15 meters per second. But remember, that 15 meters per second was a horizontal velocity. So this simply goes away. Plus 1/2 acceleration, negative 9.80 t squared. Now, that describes the height at any time. But we want to know what time it hits the ground. Well, when it hits the ground, that means the height is 0. So I put a 0 in here. 0 equals 44 minus half of 9.80 is 4.9 t squared. I do just a tiny bit of algebra, move the 4.9 to the other side, and I get that t is 3.00 seconds. They gave me 3 significant digits, so I'm going to keep 3 significant digits. That's my flight time. So t is 3.00 meters. 3.00 seconds. Now I can answer a couple of questions. I can figure out how far it travels horizontally. I can figure out how fast it's going to be going when it hits the ground. Let's start with how far it travels. If I want to find the range, that's another word for this distance, I have to use horizontal motion. Horizontally, this looks like this. Same equation. Only now, I'm only interested in what's going on horizontally. Well, think back. Horizontal acceleration is 0. That's going to go away completely. This is also 0. So horizontally, we're basically left with our position is equal to the initial velocity times the time. And the initial horizontal velocity is 15 meters per second. So I have 15 meters per second for 3 seconds. And I see it can travel 45 meters. This equation is that old middle school equation that says the distance equals the rate times time. If you want to know how far you travel, multiply your speed or your velocity times your time. As long as there's no acceleration, that distance equals rate times time. It works great. So it's going to travel 45 meters. The only other question we really could talk about is how fast will it be going when it hits the ground? Well, that we need to think about. As it's traveling, it's gaining speed. In fact, right when it hits the ground, it will be going its fastest. Now, the horizontal speed is going to be constant. There's no acceleration. So at t seconds, the vertical velocity is going to be 15 meters per second because that does not change. But vertically, we have to go back to the fact that velocity is v0 plus at. So if we want to look at the y, Vy is going to be 0. It did not start with any vertical velocity. Minus 9.8 times 3 seconds. And that's negative 29.4 meters per second. So I know that horizontally it hits the ground with this speed. Vertically, it hits the ground at this speed or this velocity. The negative indicates, of course, that it's fallen. How do you put those together? Well, that's actually pretty easy. That's just a vector sum. You've got 15 meters per second this way. You've got 29.4 this way. And you can see that sum right there. Anytime we add horizontal and vertical components, it's just the Pythagorean theorem. The magnitude of the velocity, 15 squared plus negative 29.4 squared. Take the square root of that, and it comes out to be 33 meters per second. Now, we also have a direction, and we can look at this, and we can look at this picture. We can see this is going to be a quadrant 4. Quadrant 4 is when x is positive and y is negative. We don't have to add 180 degrees. All we've got to do is do our tangent inverse. Theta is the tangent inverse of y over x. So negative 29.4 over 15. It comes out to be negative 63 degrees. So the answer to the final velocity is this at an angle of negative 63 degrees. Now, occasionally students read the question and it says, how fast was the rock going when it struck the ground? And they write 0, because when it strikes the ground, it's going to stop. But what they're really asking is, how fast was it going as it struck the ground? So think of that as being infinitesimally close to having a speed of 0, right before it strikes. Okay, so just read that carefully. I'm never going to ask you, how fast was something going when it was hurtling to the ground, and want you to write, oh, when it hit the ground, it was going 0. After it hit the ground, it was going 0. But just before it hit the ground, it was going pretty fast. Perfect little example of how to add two vectors, how to think about the direction. All right, let's work with one more problem with a horizontal, just to have the practice. And we'll work one where we are given as maybe a slightly different problem. This problem says that a cannonball is launched horizontally from the roof of a building, and it lands 4.5 seconds later. So far we know this. It's launched horizontally. They don't tell us how fast, so we can think of this basically being as v0x is a question mark, but v0y is 0 because it is horizontal. We know that. And it lands 4.5 seconds later. So we know that our flight time is 4.5 seconds. It goes on to tell us that it lands 36 meters from the base of the building. In other words, they're telling me that X is 36 meters. So if we draw this picture, it doesn't tell me the height. That's going to be a question mark. Doesn't tell me the initial velocity. But it tells me this. It tells me that this range was 36 meters. So if this is 0, this is 36. And they tell me how long I'm in the air. This is an awful lot like the problem we just worked, only we're starting with the answers instead of the question in a sense. We're working from a different set. Now, okay, if I know time and I know distance, I can use this fact. I'm going to write the whole equation, even though I know we're not going to use most of it. All right. We didn't write down our accelerations, but we know those. AX is 0, AY is negative 9.80 meters per second squared. In other words, I know horizontally this goes away. I don't accelerate. I also know I start at 0. So my equation just looks like this. For horizontal motion, it's just distance equal rate times time. There's no acceleration. So 36 equals the initial velocity. The time was 4.5 seconds. 36 divided by 4.5, and I get 8. So it was thrown at 8.0 meters per second. The other question, and we could have answered it first, this one I could have, was how high was it? What was my initial height? Well, y equals y0 plus v0 yt plus 1/2 at squared. Now, vertically, the thing that goes to 0 is initial velocity. All right, I know the final height was 0. I don't know the beginning height. That's what I hope to find. 1/2 a, that's negative 4.9. And they told me the time. The time was 4.5 seconds, so 4.5 squared. I just have to follow, I just need to know what 4.5 squared is times 4.9. 4.5 squared times 4.9 comes out to be 99. Y0 is 99 meters. So they gave us a little bit different information, so we solved it. Same equations, we just had different things to look for in that problem. All right, when things are launched horizontally, it's pretty easy because we know the initial velocity in the y direction is at 0. It's exactly like free fall. It's just like we dropped it and it fell down as far as vertical motion. Let's look at something when we launch at an angle. Launching at an angle. Okay, what's that look like? Well, it looks something like this. It could start on the ground, but it could start on the top of a building. We really don't know. But we have some initial height. I'm going to call that y0. The height could be 0, could start on the ground. And then they launch it. with some velocity, v0, and they launch it at some angle, theta. And this time, we see more of the parabola. If they launch it from the ground, like this, draw a different picture, we might see the entire parabola. Okay. When we launch at an angle, some things don't change. If we think in terms of what's going on, the acceleration horizontally is 0. The acceleration vertically is negative 9.0 meters per second squared. But the initial velocity is different. I have to take v0 and get the x and y components. There's a horizontal and a vertical component to the velocity. So v0x is v0 cosine theta. The vertical component is v0y, and that is v0 sine theta. Usually we still have these problems set up where we consider the initial horizontal position to be 0, and y0 is the height. That could be from the ground, it could be 0, it could be up on the top of the roof, we really don't know. But those are what our initial conditions are going to look like. The really important thing here is don't start solving a problem where you launch something at an angle without getting that initial velocity into x and y components. We've got to look at the components. All right, let's do a problem. So we've got a cannonball. Launched from the ground. In other words, y0 equals 0. I don't really know how you launch a cannonball from the ground. It's easier if we kick a football from the ground. But we're going to assume that we have an underground cannon. So only the barrel's sticking up out of the ground so we can launch it from the ground height. It's launched with a velocity of 25.0 meters per second at an angle of 53.1 degrees. We measure from horizontal, so you can think of this as being above horizontal. But they might not write that most of the time. So if we do a picture of our problem, we're launching from the ground, 53 degrees, so we'll over 45, 53.1 degrees, 25 meters per second, and it does this. Now the nice thing about launching from the ground is we're going to have symmetric motion because we know that the time it takes to rise to its maximum height is going to be the same amount of time that it takes to fall back to the ground. Why? Because we did it when we studied free fall, and this is exactly like a free fall problem where something's thrown straight up. The only difference between the problem where it's thrown straight up and falls straight down is it also happens to be going horizontally at the same time. If we want to think about all the things we know, no horizontal acceleration. This is the important one. We need the velocity, the initial velocity. It's v0x or 25 cosine 53.1. V0 in the x direction. If I do 25 cosine 53.1, it comes out to be 15 meters per second. Position at 0 is 0. We're going to start here and end someplace over here. All right. Vertically, looks a lot the same. Acceleration still negative 9.8. But now we need to consider our initial vertical velocity. That's going to be 25.0 sine 53.1 degrees. We always use sine to get vertical components, cosine to get x. 25 sine 53.1. That comes out to be about 7. Oh, something got punched in my calculator wrong. Ah, it sure did. I was in radians and not degrees. Guys, be really careful when you type things in a calculator that you're in degrees. 25 sine 53.1. That comes out to be 20.0. Thank goodness. That was the answer I was looking for. And in this case, we're starting from a height of 1. So we have all of our conditions. Again, there's lots of questions we might want to answer. We might want to know how long it's in the air. We might want to know when it reaches its maximum height. Right here. Let's start with maximum height, because that's kind of a fun question. The maximum height happens when Vy equals 0. Because look at it. When it's at its maximum height, it doesn't have any velocity that direction. Remember, velocity is tangent to the path. So at that particular point, the velocity is this direction. Later down here, the velocity is at some angle. Okay. When does Vy equal 0? Well, Vy equals V0y plus AT. So if that's 0 and that's 20, excellent. It looks like it's going to just be a tiny bit over 2 seconds. So when I worked it, I've got 2.04 seconds. I'm going to write that down. So here's what we know so far. That time for the maximum height, we got 2.04 seconds. Well, maybe that's not the time you're most interested in. Maybe you want to know the whole flight time. Let's look at the whole entire flight time. To look at the whole flight time, I'm going to say y equals y0 plus v0t plus 1/2 at squared. If I'm looking for the whole flight time, I'm looking at this point. Well, at that point, y is 0. The initial height was 0. The initial velocity in the y direction was 20. 20 times t, 1/2 of negative 9.8 is minus 4.9 t squared. Okay, I have a little tiny quadratic to solve. This is one I can actually solve by factoring. I have one side is 0. I can factor out a t and get 20 minus 4.9 t. Anytime you solve a quadratic, we expect to get 2 solutions. In this case, the first solution is simply that t would be equal to 0. Well, it's true. It does have a height of 0 at t equals 0. That's this point. T equals 0, height equals 0. The other one is 20 divided by 4.9. It's 4.08. That's the time right there. I did that because I want to point out something. The maximum height was at 2.04 seconds. The total flight time was 4.08 seconds. Since I knew it was being caught at the same height or landing at the same height it was launched, I really could have done this just by saying, oh, I just need to double this, I'll have the time. Or if I've already calculated the total flight time, I could go, it's going to be half of that. So the total is 4.08 seconds. But I wanted you to see how consistent our results would be. However, whichever approach we used, it makes perfect sense. Let's go back to the idea of maximum height. We haven't said what that maximum height will be, but if I want it, I'm going to use this time y equals y0 plus v0 yt plus 1/2 at squared I. I want to know this height. Remember, this function describes the height at any time at 2.04 seconds. Well, it started at the ground with an initial velocity of 20 times 2.04. 1/2 the acceleration is negative 4.9. 2.04 squared. Don't forget to square it. I put that in the calculator. 20 times 2.04. Notice this part would tell you how high it would go if you could turn gravity off, if we got rid of acceleration, but we can't. I'm having trouble typing this one. 20 times 2.04 minus 4.9 times 2.04 squared. I get 20.4 meters. That actually seems really reasonable, that in 2 seconds that's how far it could go. So we know the maximum height. Another question we might want to ask is, what is the range? How far did it travel? We know how high it went. How far did it travel? Well, that horizontal distance or range, we have to go back to x. So we go back to using this information. And once again, we go, oh, well, if I'm doing x, my acceleration's 0, my initial position, I just need this. It's traveling 15 meters per second for a time of 4.08 seconds. 15 times 4.08, I get a distance of 61.2 meters. Okay, really important that you get these two velocities first. Find out the horizontal component of the initial velocity and then find out the vertical component. Really important that you remember, if you're working horizontally, you always use these numbers. If you're working vertically, you always use those. Don't mix them up, because that's probably the biggest mistake that I see. Let's do one more example. And then I'm going to leave you after this one more example with a problem I want you to think about before we get together for our class meeting to talk about all of this. Let's do Here we have my favorite. It's the human cannonball problem. It says that Lucy is launched from a cannon at a speed of 15.0 meters per second at an angle of 45 degrees from a height of 30 meters above ground. Where should her friends put the net to catch her? The net is 1 meter above ground. This is slightly different than the one in your notes, because in the one in my notes, I let the net be at ground level, which meant you had to dig a hole and put the net, but I think we just put it above ground. So here's our situation. She starts 30 meters above the ground, right there. She's getting launched with an upward velocity of 15.0 meters per second, above horizontal. She's going to go up, and she's going to come down. If her friends put the net at the right place, here's the net, she's going to have a height of 1 meter when she hits the net. Here she is, human cannonball. She's probably all balled up, but I can only draw stick people. When she lands, what do we want to know? We want to know this distance, the range. I can't get the range until I know for sure how long she's in the air. So it's going to be a question of solving for time. Anytime we launch something at an angle, we really want to be sure we get those horizontal and vertical components. I'm going to erase part of the problem because you have the problem drawn out now. And let's just start thinking about what we know. We know she starts with an acceleration is going to be 0 horizontally. V0x, I've got to do 15 cosine 45. I do have 3 significant digits, but let's just do 15 cosine 45. It comes out to be 10.6 meters per second. And of course, she starts at 0. This is negative 9.8. If I do 15 sine 45, that also is 10.6 meters per second. At 45 degrees, your x and y components are the same. You're going just as much up as you are over. And of course, the acceleration. The initial height in this case, it says, is 30 meters. She starts out 30 meters above the ground. We got to find the time, and then we'll find the range. Time, horizontal question, vertical question. Time is always a vertical question, okay? Time is the vertical motion is what causes you to fall and hit the ground. So y equals y0, v0 yt plus 1/2 at squared. Okay, we want to remember, we want to find at what time her height will be 1 meter. We don't care where she hits the ground because she's not going to hit the ground. So we can't use y equals 0. We actually want to put in her 1 meter here, our 30 meters here, 10.6 t. Now this is a positive 10.6 because she's going up, but this is a negative 9.8 because acceleration's down. Guys, this is a quadratic equation, and it's not going to factor, and it's not going to be overly, terribly easy. I can solve it a couple of ways. I'm going to put everything over on this side. I'm going to get 4.9 t squared minus 10.6 t minus 29. That's my equation. Remember, I had a 1 here, so when I move that over, the easiest way, I think, to do this is in a graphing calculator. I'm going to graph two equations. I don't know if you'll be able to see this, but I may try to hold this really close to the camera so you can. Turn my calculator on. I'm going to graph this first equation, this part in y1. And I'm going to try graph that y2 is equal to 0. And then I'm going to look for the intersection. There is another way to do it. I can actually just look for a 0, but I'm going to do it this way. So y1 is 4.9. I don't have a t, I have an x. That's okay, I put x squared. Minus 10.6x minus 29. In y2, I'm going to put 0. Let's see if I can make this where you guys can possibly, I don't know that you can see any of what it says. I'm trying to see if I get it at an angle, I can make it show up. Oh, almost. Okay, you can almost see it right there. There's my two equations. I'm going to graph them. Now, there's a good chance when you hit graph, you won't see a thing because this problem starts at 30 meters. Your window may only go up to 10, so I'm going to have to kind of change my window a little bit. When I get it graphed, I do see graph, but I'm going to have to adjust my window. Trying to see if I can figure out what angle to the camera I can get rid of that glare and you can see it. Apparently not one. I'm going to have to make my window a little bit bigger. I'm going to let my negative y go down to negative 40. If you have a color calculator, it's really nice. My parabola is blue and my y2 equals 0 is red. And I just have to find an intersection. An intersection, you press second trace. The blue says calculate, that's what I'm trying to do. I want to find the intersection. And I want to find this intersection on the right here. Inner. They intersect at t equals 3 point, so I'm going to solve this. Intersect at t equal 3.7440. I kept a lot of places because I want to get my net in exactly the right place. So I know this is my time. She's going to, at that time, she's going to be 1 meter above the ground. What horizontal distance corresponds to that time? You can probably stop writing these terms you know are 0 as soon as you're comfortable with their 0. This is just going to be x equals v0xt. She's traveling 10.6 meters per second for 3.744 seconds. 10.6 times 3.744. And I want to put that at 39.7 meters. If her friends can do the physics, they're going to know where to put her net, so poor Lucy will be okay. Now, if Charlie Brown and Schroeder are doing it, she may be in trouble. I don't know. All right. I want you to think about one more problem, but I'm not going to work it today. I just want you to think about it. If you're really ambitious, you can probably get on the internet and find the solution and figure it out. But think about it first. It's a very common physics problem. So we consider a classic problem. It's called the monkey chute problem. Now, when I was a student, the problem said, a hunter shoots a gun at a monkey in a tree. The sound startles the monkey so that it falls from the tree the instant the gun is fired. Where should the hunter aim to hit the monkey? Assume neither the bullet or the monkey hit the ground first. Now, since then, the problem is often phrased like this. A zookeeper shoots a banana gun at a monkey in a tree. The sound startles the monkey so that it falls from the tree the instant the banana gun is fired. So if you want to not worry about injuring your monkey, you don't have to. Where should the zookeeper aim to hit the monkey? So here's our problem. We've got a tree. Should get some green, do a little artwork. Hanging from one of these branches in my tree is a monkey. There's our little monkey tail. There he is. He's holding on for dear life. Somewhere over here, I have a hunter. This hunter is holding a gun that will shoot either a banana or a bullet, depending on your sensibilities. And the question says, where should he aim? I'll give you some hints. When I solve this problem, I'm going to say the middle of the monkey is H. I call this the height. I call this distance S, this theta. And all I know is the monkey's going to fall, and I want the monkey and the banana to be at the same height at the same time. It's a great problem. Give it some thought. It's going to take a little bit of knowledge of trigonometry. It's going to take a little bit of knowledge, or a fair amount of knowledge of projectile motion. I'll see you guys in class to talk about it.